Welcome back. For continuation of optimization problems, you're going to find these are very similar to the ones we have already completed. Not too challenging yet. We're going to deal with just a different function. We're going to talk about cost, and you see that there's money involved here. So we have a box. It says it's a closed box with a square base, and it has to have a volume of 252 cubic centimeters. To create this box, the material that's used for the bottom costs 5 cents per square centimeter. The top costs 2 cents per square centimeter, and the 4 sides costs 0.03, 3 cents a square centimeter. We're supposed to find the dimensions, meaning the length, the width, and the height, so that this the cost of creating this box is a minimum. So again, I'm going to begin by labeling my dimensions. So I will call the width X and the depth or the length X because it's a square base. And then again, I will refer to this as the height right here, this bottom to top. Now I will start by following these steps as I always have. I will begin by creating the equation of constraint and then the equation that we're minimizing. So the equation of constraint is a volume, and the formula for volume, 252, is x squared h, length times width times height. That's my equation of constraint. I'm trying to minimize cost, so what I'm going to do is calculate the total cost of building this box with these dimensions. It says that the bottom costs 5 cents per square centimeter, and the area of the bottom is x squared. So it's 0.05 times x squared. Then it says the top costs 2 cents a square centimeter, and the area of the top is also x squared because the bottom and the top are both the same size. Now, we have to then get the area of the sides because each of the sides, it costs 3 cents per square centimeter. And the dimension of any side is x by h, and there are 4 such sides. So you have 4xh, and then it's 3 cents per square centimeter, so 3 cents times the area. And so the cost function, well, we can combine like terms if we simplify this, and then we can multiply 4 by 0.03, and that's your function that you're trying to minimize. So the next step says isolate for a variable using the equation of constraint. So I'm going to isolate for h. So I get 252 divided by x squared is my height. The fourth step says substitute that into the equation that we're minimizing in order to guarantee that this equation has only one independent variable. So when you simplify the equation, 0.12 times 252 is 30.24. So you get 30.24. Those x's cancel out. And I bring the x up because I don't want any rational expressions. And now I have the function the way I like. So step 5 up here says take the derivative. That's what I'm going to do. And I get 2 times this is a mistake, this should be a 7. 0.05 plus 0.02, sorry about that, is 0.07. I bring the 2 in front, I get 0.14 x squared minus 30.24x to the negative 2. I then set the derivative equal to 0 and solve. Remember, here's that classic negative exponent, which is always going to happen, so I'm going to multiply everybody by x squared and get, this should not be here, and get x cubed here, and then 30, this disappears. So the derivative is 2 times 0.07 is 0.14, and then you drop the exponent by 1. Multiply everybody by x squared. I solve. 30.24 equals, oops, I forgot the 0.14, x cubed, sorry. I then isolate by getting 30.24 divided by 0.14, and that is x cubed. And so the solution for x is the cube root. And if I punch out 30.24 divided by 0.14, well, I get a lovely number. I get a nice whole number, which isn't common. Now the question says find the dimensions. So I've already got the 6, so I know it's 6 by 6. I just have to solve for h. Again, where the derivative equals 0, I'm confident is going to be a minimum because of the way they set up these questions. We're cheating. So I push that back in over here, and I get h is 252 over 6 squared. And when I punch that out, 252 divided by 36, get another beautiful number, 7 centimeters. So the dimensions that minimize the cost would be 6 centimeters by 6 centimeters by a height of 7 centimeters. Easy peasy. Same process. It's just you have to create the equation of what they're minimizing, and that's what can change from one question to another. Now we're going to do another question, which is similar to the example that I illustrated at the very beginning of the first video. And these are the homework questions that match this kind of an example. We're going to do this kind of a question, and then these homework questions match this type of question. And this is the first question I think you're going to hit that really will give you a challenge. But let's take a look at this. It says a farmer has 800 meters of fencing, where have I heard that before, and wishes to enclose a rectangular field. But one side of the field is alongside a road, and there's already fencing there. So it means he only needs the 800 meters to enclose the other 3. For example, if this is the road, he only needs to put fence here, here, and here. And that's his 800 meters of fencing. So it says, what should the dimensions of this field be? In other words, find the length and the width to make sure the area is a maximum. So I begin by writing the equation of constraint. Now I need to put variables in to represent, so I'll call this L for length and W for width. Again, by putting my variables in the diagrams, that is a way of defining the variable. So it's not necessary to make a statement in addition. Whenever you do not create a diagram, I would ask you to define your variables. So the equation of constraint says that this has to be 800 meters. So that's W plus L plus another W has to be 800 meters of fencing. That's your equation of constraint. The equation of what you're maximizing is area. So area is simply length times width. And again, I point out that the equation of constraint always has a number. The equation of what you're trying to maximize doesn't. It always has a variable. But we're going to do step 3, which says isolate this. So I'm going to get it in the form L equals 800 minus 2W, so that I can substitute this expression into the function I am maximizing. He places the L to guarantee that I have my equation in one independent variable. I then simplify it. This is a real easy one from an algebra point of view, and there's the function that you're maximizing. How do you find the maximum? Take the derivative and set it equal to 0. This is super easy because what happens is you get W is 200. What that means is that your fencing would have 200 meters on each side, and that would leave another 400 meters for the length. Again, you can use this formula to easily figure that out. It says, what should the dimensions be? The field will be 200 by 400 meters. It's a pretty easy question, but it just gives you an idea of how the 6 steps that we've outlined can be followed for every question. So your next batch of homework questions comes from these and these. This one is interesting at a minimum, okay? And that's it for this video. See you in a few days.